No. So we need to know a little bit about circles, okay? So if you have a circle, okay, right? You guys know, like, if you have a radius, it's like the same distance the whole way around, yeah? Okay. If I have a line that goes through the center of the circle, okay, a straight line, yeah? That's called a diameter, yeah? Yes?
Yeah.
Okay. And something kind of nice happens whenever you have a diameter and you have any other point on this circle, okay? You always get a 90-degree angle, like that. Okay? And this is called Thales' theorem. Don't worry about what it's called, because I didn't even know the name of this for like 40 years, okay? So, but sometimes it's easier to say Thales' theorem than be like, oh, there's a circle and there's a line, and just like try to explain to someone what that means, okay? So it's easy to remember two words. Okay, does anyone know how to prove this? So you know what my claim is? My claim is this angle is 90 degrees, okay? Yeah? It's always 90 degrees, no matter what, okay? Does anyone know how to prove this? Okay, let me show you a proof, okay? So what you do is, so we're not going to assume it's 90 degrees, okay? Because we don't know that yet, okay? And what we're going to do is draw in the radius here, okay? You see? Okay, and we know the radii, these are all equal lengths, right? Yes? So that means these are all isosceles triangles, yeah? So if I call this like alpha, this is alpha, yeah? Yes? If I call this angle beta, this is also beta, yeah? So it's just like Greek AB, yeah? That's what I'm saying? Yeah. Okay. Now tell me what alpha plus, so what's the angle, what's alpha plus beta plus beta?
2 alphas plus 2 betas.
So it's 2 alphas plus 2 betas, right?
Yes.
Yeah? Which is what?
180 degrees.
It is 180 degrees, right? Because that's a triangle, adds up to 180, yes?
Yeah.
Okay, now what?
Divide the thing by 2, so...
Okay, so there's 2 times this, right? So you can divide it by 2, right?
Oh.
So you get, if you divide by 2, you get alpha plus beta equals 90, right? See that?
Oh.
But what's alpha plus beta?
That one.
It's this angle here, right? See? That's alpha plus beta, yeah? And I just proved it's 90. Understand? So this is one of the situations where I actually give you a proof, okay? Sometimes I tell you the statement, but I don't give you a proof, right? But I gave you a proof for this. So you're meant to actually understand this, okay? So if you don't, you should ask a question. Does that make sense?
Yeah.
You get it? Okay. So that's one direction of the theorem, okay? So let me explain. There's a little bit more complicated. In logic, there's a statement and there's converse, okay? So here I have a semicircle, and I have my conclusion is 90 degrees, yeah? The converse is if I reverse that, okay? So what if I had a 90-degree angle, yeah? Can I conclude it's the diameter? Does that make sense? So if I start like this, if I have a circle and I have an angle that's 90 degrees, yeah? Yeah? Can I conclude that this passes through the center? Does that make sense? So that's the what's called the converse of the statement, okay? Now, the great thing the interesting thing about geometry is that the converse tends to be true for a lot of things, okay? Whereas in normal everyday logic, the converse may or may not be true. Does that make sense? So like, if it's raining, I'll bring an umbrella, but if I have an umbrella, then it's raining. Like, if I have an umbrella, it might not be raining, you understand? So the converse is not necessarily true. Okay? I might have the umbrella just because I want to protect from the sun. Okay? But in geometry, for some reason, a lot of the time it is true. Okay? So here, how can we conclude that it's the diameter? If all we know is 90 degrees, yeah? How do we know it passes through the center? Okay? Does that make sense? So what we can do, okay, is we can sort of imagine, so the center is here, right? Yeah? If I join this line, okay, it could just happen to hit that other point, right? Then there's nothing to prove because it's already passing through the center, yeah? So what happens if it doesn't hit the point? What if when I pass through this line, it hits like over here? You know what I mean? Does that make sense what I'm saying?
Yeah.
So what if the center was like there, and then when I join it, it doesn't hit this point, but it hits somewhere else? Yeah? Okay. Well, then what I can do is I can join this point to this point here. Okay? Yeah? And when I join that, I know from what I just proved that this angle should be 90 degrees, right? That makes sense? Okay. But the problem with that is this angle we already said was 90 degrees, right? And it's clearly smaller than the angle we just made, yeah? So that's a contradiction. It can't happen like that, right? So actually that proves, and if you put it on this side, it'll be bigger. So either way, it won't equal 90, okay? So actually, so it actually forces this to connect to here exactly. Does that make sense? Yeah, and usually, so the crazy thing about geometry, not only is the converse true, you can use the original statement to prove the converse is true. Yeah? So it all seems a bit paradoxical, right? Okay, so we'll give you a chance to ask about this. So do you understand what's going on with this? How we proved if we start with 90, it has to be a diameter. Does anyone not understand this? I know at least like 2 of you don't understand this. Alright, so basically what's going on is, so the question starts with the assumption that this is 90 degrees, right? So if this point does not make a diameter with this point, then what we have is we have another angle that's 90 degrees because we know every semicircle makes 90 degrees from this, right?
Yeah.
But this angle is bigger than this angle because this angle is smaller, right? But we already said this angle is 90 degrees, okay? So in fact, it actually has to be this point because that's the point that makes the same angle with that, you know?
Yeah.
Alright. Okay. So actually, the only thing you need to know for this problem is that fact, okay? And the stuff about area of a triangle you already know, okay? Like area of a triangle is half base times height, yes? Everyone knows that, right? So only to those 2 things you can solve this problem with. You understand? I'll give you a little bit more time. Okay, so I'm going to give you a hint, okay? So if you think about it, right, like I just told you something you didn't know, right? So it could be that one of the reasons you couldn't solve the problem is because you didn't know that, right? So one thing you might look for is how that applies to the problem. That makes sense? I mean, that's unique to the context of me giving you that particular hint, but I think that's a good thing to think about, right? So I want you to tell me how Thales' theorem that I just told you, right, is present in this problem, okay? I don't need you to solve the problem. I never need you to solve the problem. The whole point of the whole point of the problem is it can't be solved in one step. You understand? If you can solve it in one step, then there's no point really doing it. But what we can do is we can find how Thales' theorem is in this problem. And that could be one step. Does that make sense? Yeah? Okay, I'll give you a good at least 5 minutes to tell me, okay? And if no one gets it, I'll give you a bit more time. Okay, I'll give you one of them. You have to find the other one though, okay? So, I mean, isn't it amazing? I told you what Thales' theorem is. You all said you understood it, but we can't see how it's here, okay? So there's something about... so that's a skill, that's definitely a mathematical skill, okay? So maths is about... even understanding anything is about relating things to each other. Do you understand? You're relating things to other things, yeah? You never really understand something on its own absolutely, okay? And if you can do that, you should be able to relate that to other things, okay? So let's look at this picture. So we'll say what Daniel already said, okay? Can you see there's a 90-degree angle here at C? Yes? Yes? Okay, so remember Thales' theorem talks about 90-degree angles on circles. Yes? Okay. So what Thales' theorem actually tells us about this situation here with the 90 degrees at C, yeah? What does it tell us?
QP somewhere it comes to the center.
So QP is a diameter, right? So that was the point of what I was saying before. Remember?
Wait, because I think that's
Be quiet. So it's the converse. It's the converse of having a semicircle and 90 degrees, right? If you have a 90 degrees, then this is a semicircle. Does that make sense? Alright. So, can you please find the other one for me? And the only one who's not able to tell me this is Daniel, okay?
Why? I just...
Alright, does anyone want to volunteer, or I'm going to ask Jaden. Alright, Jaden, what's the other one?
I think CRH, because H is 90 degrees and it has, and C and R are like points on the circumference.
Yeah, see, we're not asking for anything spectacularly difficult, right? We said, look, so Thales' theorem talks about 90-degree angles on circles, yeah? There's only one 90-degree angle here, and there's only one other one here, you see? See, do you understand that's 90-degree angle? So that's what altitude means, right? Altitude means it makes an angle of 90 degrees with the base, yeah? And so because this is a 90-degree angle on the circle, it means CR has to be a diameter, right? Okay. So let me draw that in, okay? So this is like, what would you call this? This is called like, so if you found the C, it might be difficult because, so you're in a situation where you found one instance of it, but not all instances of it, okay? But now we have all instances of it, okay? So we can follow this lead, do you understand? It's like a murder mystery, you know, you follow the lead, right? It's like, so this is a diameter, yeah? So CR is a diameter, yeah? So that means it passes to the center, yeah? Okay? QP is also a diameter, okay? This also passes through the center. Does that make sense? Yeah? Okay, I want you to tell me something about this that you didn't know before because you didn't know it was a diameter, right? That's the hint. You understand? And then we move on from there, okay? You understand what I'm saying?
I understand.
Daniel, you're so annoying. Okay, now Alvin is back. Let me really focus you on what I want you to see something, okay? Okay. Let me just focus you on this shape here.
Oh, the rectangle.
This CP is the same as QR because CQP, because
Okay, so give you a bit of time to process this, but let me know what you see about this blue shape, yeah?
Okay.
Okay, I don't know how, but you all said it was a rectangle really quickly, yeah? Is it just because it looks like a rectangle?
Yeah.
I guess geometry is kind of like that, right? It's visual, yeah? If it looks like a rectangle, then you might, well, is it actually a rectangle, right? Okay, so who wants to prove to me it's a rectangle? Ishan? Does Ishan want to do it?
Me.
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 Alvin?
Yeah.
No.
Okay, prove it.
Because it looks like a rectangle. And also, because we already proved that CR is the diameter.
Yeah.
And that means CPR.
Yes.
What
CPR
you do to like
is a 90
someone,
degrees.
but that's also 90 degrees.
Yeah.
And we know QP is also a diameter.
Yeah.
So QPR is also 90 degrees.
Yeah.
And
QPR, you mean QRP?
QRP, my bad.
Yeah.
Yeah.
So
And
we
the
have,
other two are also, because like
That one's already given.
that one's already given and then that's
okay, so we have a four-sided shape and it has four 90-degree angles, yeah?
And
sides like what?
Does that make it a rectangle?
Yep.
Yeah. No.
No.
Well, I mean, it makes it a parallelogram at least, right?
Then the diagonal
But because it's
equal.
90 degrees, it actually is a rectangle, yeah?
The diagonals are equal.
So it's actually a rectangle, yes?
How the
And it's
hell?
a socket. Oh, I love that. Whatever. I don't know. I'm joking.
Okay. So now that we know this is a rectangle, how do we proceed from here? Okay. This is a slightly more open-ended question than the other ones. Okay, so this next one is a bit it's a bit of a different kind of step than the other ones. Like the other step is more about execution. Here it's more about understanding sort of what's going on. So I guess before we didn't have enough information to talk about the areas, right? And now we have actually almost enough information. So the goal of the problem is to compare the area with the dotted triangles to the checkered triangle, right? Yeah? So which area is bigger? Yeah? But let's have a look at these triangles. So this triangle is like this, right? Yeah? Okay. And instead of drawing the other triangle, I'm going to draw another one that's maybe more relevant, okay? I'm going to draw this triangle. I'm going to draw this triangle. So I guess my question now is more specific. So what can you tell me about these two orange triangles? Yeah? So what's so special about these orange triangles? Okay? Okay, so the hint is basically why did I choose this orange triangle, right? Like think about it. So I want to talk about the dotted triangles, yeah? Okay, so one nice property that this triangle has, okay, is that it has a side that's on this nice rectangle that we know, right?
Wow.
So the rectangle represents the things we understand in the problem, yeah? Whereas the triangles represent the things that we don't understand in the problem, yeah? So it's nice that this triangle has a side on this rectangle that we understand, yeah? Okay. But this other triangle doesn't quite have a side on the rectangle, but we just extended it so it does, yeah? So the nice thing about the orange triangles is that they both have, each of them has a side that's on the rectangle, okay? So that's the hint. So now tell me what else you can figure out about the orange triangles, okay? Okay, let me take you back, be quiet, to primary school, okay? So if you were to create a maths Olympiad problem in primary school, what would it look like? Okay, it would look something like this because the only thing you know in primary school is the area of a triangle, right? What is the area of a triangle? Well, it's half the base times the height, right?
Wow.
But look at this. These two triangles have the same base, you see? Do you know the opposite lengths of a triangle are equal, right? Yes? So these two triangles have the same base, right? Does that make sense? Yeah?
Oh.
Okay, and what's the height of these triangles? Huh? What's the height of these triangles? Let me just pause it there. I'll give you
The orange ones?
Yes, the orange ones. So the height of these triangles, right? So it's like height is like, you know, if you made the base longer, right? Whatever this 90-degree line is, yeah?
Yeah.
That's the height, yeah? Okay. So it's the distance to the base, yeah? Okay. The thing is, we don't necessarily know where h is. We don't know what the heights are, yeah? But the thing is, we know what they add up to. You see? See? So if we draw a line there, right? We know that this is the height for one of them, yeah? And that's the height for the other one, yeah? And if we add up the heights, we get the length of the rectangle. You see that?
Oh, so smart.
Does that make sense?
Yeah.
Yeah? Wait, does that make sense? Alright. That's good. We're all on the same page now, okay? So we don't, and so that gives you, that kind of makes sense now why they talk about those two areas together, right? Because we don't necessarily know what the areas are separately, but when you add them up, you know what the areas are, right? Because if you do base times height plus base times height, it's the same as base times the sum of the heights, right? So what is the area of the orange triangles then added up? What is the area?
The rectangle?
In terms of the length and the width of the rectangle.
Well, I'm thinking half the thing.
So what's the area of the orange triangles in terms of the rectangle?
I got it.
Okay, what is it?
So you said that the height in total, the two heights were the length, right?
Yeah.
And then the two blue ones are the base.
Yeah.
So it's the length times 2 of the base. No, sorry. What? It's the length plus 2 of the base.
No, gosh.
So what is the what?
It's base times height over 2 plus base times height over 2, yeah?
Yeah.
Which is base times the sum of the heights over 2. So it's base times length over 2, yeah? So the sum of the two orange... Alright, so let me just... The sum of the two orange things is equal to half the area of the rectangle, okay? Okay, so let me just re-summarize this very important point, okay? Let's call this the base, yeah? Yeah? So, and then we'll call this the height. Height 1, and this is height 2, yeah? And we know that height 1 plus height 2 equals the length of the rectangle, yeah? Okay. So the areas of the triangles is base times height 1 over 2 plus base times height 2 over 2, yeah? Yes?
Yes.
Because base times height, yeah? Okay. So if you add this up, they're already over 2, right? And they both have a base, so it's really just h1 plus h2, right? Yes? But h1 plus h2 is h, yeah? So this is just bh over 2. Thank you. Okay, so bh over 2 is the length times the width over 2, right? So it's literally half the area of the rectangle. That make sense?
Yeah.
So the sum of the two areas of the orange triangles is equal to half the area of the rectangle. Yeah? Okay. Does everyone understand? Yes? Okay. So that's the crazy thing about the base times height, right? Because the triangle could be some weird shape and the height's like over there, you know? Right? But it's the same as if it was over here. You know what I mean? Okay, so tell me now that you have the orange triangles, what do we do now? Okay? What do we do now? What do we do now? Okay, so I mean, I made it more open-ended what to do next, right? But actually, there's a natural thing to do next, okay? Because you're trying to look for the area, you're trying to compare these areas with the checkered triangle, right? So you want to now do something, you maybe want to now, like what you might want to do is relate the area of that triangle to the rectangle, you see? That's a natural thing to do because the rectangle is what you know and you actually related the orange ones to the rectangle, okay? And so maybe I'll give you a little bit of a hint. So I guess originally we have this triangle here, right? Yeah. Okay, but what can we do? How can we modify this triangle to something more convenient? Can you tell me?
Extend CT of the arm.
Yeah, we can extend this so, and because it's the same reason we extended the orange one, right? Okay, so now we have a bigger triangle, yeah. Okay, and so what can you tell me about the green triangle? That's the next. Okay, so this one, the green triangle, yeah, is obviously half of the rectangle, yeah.
Yes.
So this is equal to the area of green triangle.
Yeah.
Does that make sense? Okay. So now we just got to put it all together. Okay. Now I'll give you a few moments to put it all together. Okay. How are we gonna put it all together? It's all coming together now, right? All right. Finally, Daniel, you can explain
Yeah.
what you want to explain?
So you said the orange triangle is equal to the green triangle, right?
Yeah.
Which means, and they both share the white part, right?
What white part?
Sorry, TRP. the triangle.
Yeah. So he's saying, see, look.
So we cancel it out from
So the problem we had was we changed the triangle to include this bit, right? Yeah. But you can see, but they have the same component, so they cancel each other out. Does that make sense?
Which means that the orange triangle is equal to the green triangle.
So no.
Question's a trick
No.
question.
So the orange triangle is equal to the green triangle, right?
Yes.
But the green triangle with the purple bit cut out is also equal to the orange triangles with the purple bit cut out, right?
Right.
Yeah. And the orange triangles with the purple bit cut out is exactly the area that we were asked to compare, right? Yeah.
Oh yeah.
You see?
It's a trick question, guys.
And so therefore, the areas are always the same. Yeah? I think if you can appreciate the beauty of this question, I think you have a good chance to be good at maths, okay? Because see, it's not just about people coming up with clever ideas to solve the question, yeah? There's actually real beauty in whoever made this question. You understand? And that's one of the reasons we do this contest. It's actually like some of the most original and most clever made problems in the world. Okay? So it's not just like, oh, you can open any textbook and you get like some great question. You understand? But that was truly amazing, don't you think? It's a very simple idea, right? They managed to put it all into one question. You know? And that's one of the key reasons why we ran Tournament of Towns. Okay? We went through great lengths to run Tournament of Towns. Okay?
Parents